All right. This is lesson 6 in unit 3. We have been looking at consequences of the derivative, applications from a sense of consequences. And on today's show, we deal with a very big result. We deal with the second derivative test for local extrema. Two reasons. One, it is not always possible to use the first derivative test for local extrema. There are situations where we can analyze a function, but only so far. Two, we may not want to use the first derivative test. And we may not want to use the first derivative test because it might actually be easier to use the second derivative test. So today we're going to connect our knowledge of first derivative, second derivative, and the function itself with the second derivative test for local extrema, and it looks like this. This is the second derivative test for local extrema. And it goes like this. If f prime of c is 0, and f double prime of c is negative, then f has a local max at x equals c. 2, if f prime of c is 0, and f double prime of c is greater than 0, then f has a local min at x equals c. This is one of those things that almost makes sense if you think about it. I will illustrate. What does it mean to say that f prime is 0? Well, it means we've got a flat tan. This is a flat tangent line. What does it mean to say f double prime is negative? Well, it means that we are concave down. So I've got to draw a function that's concave down and has a flat tangent. If I draw a function that's concave down and has a flat tangent, we've got a max at that point. Similarly, this implies flat tan. F double prime being positive tells us we're concave up, so I've got to draw some function that's concave up but has a flat tan somewhere. If I can draw a function that's concave up that has a flat tan somewhere, that is a local minimum. So this is very useful if we know about f only at some point, but not in an interval, because this only uses information at x equals c. It doesn't use information on either side of c. Side note, the test fails. Notice the following. We have considered f double prime being negative and f double prime being positive. So the side note here, and I'm going to make good use of my board space by kicking all this stuff over to make room for my side note. The side note here is that the test fails if f double prime of c is 0, or if f double prime of c does not exist. The test fails. We cannot discern if f has a local max or a local min at x equals c if the first derivative is 0 and the second derivative is 0 or the second derivative is undefined. We can figure that out if we have other information, but we can't figure it out from f prime of an f double prime at c. So what does this look like practically? Let's find local extrema for f of x equals 3x to the 4th minus 16x cubed plus 6x squared plus 72x minus 10. 3x to the fourth minus 16x cubed plus 6x squared plus 72x minus 10. If I've got this right, I know what f prime is. That's 12x cubed minus 48x squared plus 12x plus 72, which happens to factor, not that I expect you to know how to factor a cubic, but it does factors very nicely. So I know on my number line, there are 3 points of interest. -1 is a point of interest, 2 is a point of interest, and 3 is a point of interest. Those are x values where I could have mins and maxes. There's no place where f prime is undefined, so the only 3 critical points are at -1, 2, and 3. So let's go to f double prime. F double prime is 36x squared minus 96x plus 12. So what I'd like to do is I'd like to find f double prime at -1, f double prime at 2, and f double prime at 3. And I can do that just by substituting -1 into f double prime, substituting 2 into f double prime, substituting 3 into f double prime. And I get 144, -36, and 48. So what does that tell me? At x equals -1 and x equals 3, I have places where the tangent line is flat and the second derivative is positive. So we're concave up at those places. This is a min. This is a min. At x equals 2, I have a flat tangent and I'm concave down. So if I'm concave down with a flat tan, that's a max. So f has local mins at -1, comma, whatever you get when you sub in -1. That's 9 minus 10 is -1, minus 72 is -73, plus 16, -57. And at 3, comma, oh boy, whatever f of 3 is. Great. F has a local max at 2, whatever f of 2 is. Maybe I can pull that off. 48 minus some obscenely large number is -60. Plus the 144 is 84 minus 74, so that middle term plus 24, 98. And that's what the analysis looks like. Consider the following. Let f prime of x be 3x cubed plus 9x squared. No. No. We'll do that. We'll do that. I want to identify extrema. I want to find intervals of increase and decrease. And I want to find intervals of concavity. Hopefully culminating in a sketch of what f of x is going to look like. Because f of x is off screen. F of x we don't know. But we can find where the possible extrema are. And how do we do that? Well, we take the derivative, which is 4x cubed plus 8x squared, and we set that equal to 0, and lo and behold, there are two possible extrema, two possible extreme value locations. One is at x equals 0, and the other is at x equals -2. So that being the case, we can set up a number line, which is we've always said is a line with numbers on it, and figure out that f prime is negative for x less than -2. That's not hard to see. And then it's positive again, and then it's positive. F prime is 0 at -2 and at x equals 0. But in between -2 and 0, f prime is positive. You can confirm that, sticking at your favorite number into f prime. And when x is positive, f prime is positive. So what do I know? I know that f prime at -2 changes from decreasing to, no, I'm going to try that again. F prime changes from negative to positive, so f changes from decreasing to increasing. X equals -2 is a min. At x equals 0, we go from positive to positive. F prime stays positive. It does not change sign, and so there is neither a min or a max. So there is only one extremum, and that is the local min at x equals -2. Now we could have confirmed that. We could have said, here's f double prime. F double prime is 12x squared plus 16x. If you take f double prime at 0, you get 0. Second derivative test fails in that case. Does not hold. So we have to use the first derivative test on this particular function because of that. Naturally, f double prime of -2, that's, oh boy, that's some positive number. That's 48 minus 32, 16. 16. And so we've got a flat tan and we're concave up, so we've got a min at that point. Intervals of concavity, well, if I were to factor like so, we would figure out that at x equals 0 and at x equals -4/3, we have the possibility of inflection points. And sure enough, both of those are inflection points because the second derivative changes sign at those places. F double prime changes sign at x equals -4/3 and at x equals 0. And therefore, we have inflection points on the graph of f at -4/3 and at 0. So what does this look like? Well, we know that we're concave up because we've got a min at x equals -2 at that point right there. And then at x equals -4/3, we've got an inflection point, and then we're concave down until x equals 0. We're concave down till there. Then f prime is positive and f double prime is positive, which means that we're increasing and we're concave up. So the graph is going to look something like that. We don't have f of x. We don't have what the y values are specifically, but we know that the graph is going to be some vertical shift of that thing right there. Excellent. Excellent. One more thing to put it all together. Consider the following. I'm going to give you information about f prime and f double prime. And we're going to try this thing. We're going to try, oh boy, let's say from -3 to 0, and then at x equals 0, and then from 0 to 3, and then at x equals 3, and then from 3 to 5, maybe. Maybe. And so it goes like this, and it goes like this, like so. If f of -3 is 4, and f of 5 is 0, sketch a possible f a possible f, because there will be many. So 1, 2, 3, 1, 2, 3, 4, 5. Those are the big spots we're looking at. At -3, the y value is 4. And at 5, the y value is 0. So between -3 and 0, f prime is positive, f double prime is positive. We are increasing and concave up. We are increasing and concave up as we approach a place where neither the derivative nor the second derivative exists, which means we are approaching a place where there is a vertical tangent. We are approaching a place where the tangent line is vertical. Then between 0 and 3, f prime is negative and f double prime is positive, which means that my function is decreasing and concave up. So we're decreasing and concave up to here. And we're approaching a flat tan because at x equals 3, the function's derivative is 0 and its second derivative is 0. So at x equals 3, we've got a flat tan. And then between 3 and 5, f prime is negative and f double prime is negative, which means that f is decreasing and concave down. So I draw a decreasing concave down graph, and I get something that looks like that. I mean, there are obviously multiple forms of that correct answer, but they all have to look something like that. So what happens to us? We have to be able to analyze a function using its first derivative and its second derivative, or both. And if we can do that, we are in very, very good shape. So where the course goes from here for the next few days is we do a lot of work with optimization, which uses the first derivative and second derivative to figure out in geometric contexts what's the biggest something can be, what's the smallest something can be, and that's where we head starting tomorrow. Thanks, everybody.